All right, welcome to chemical kinetics, our next topic. A little disclaimer, there could be a few mistakes as I talk and go over this, but at least we'll go over it in class together to make any corrections or whatnot, because, yeah, I don't want to record this 14 times, like right now making a mistake, but okay. All right, this first one we're getting into is kind of a review of things that you saw in your first year of chemistry. Yes, last year during kinetics, you guys were distance learning. So we're going to kind of go over a few things we've already seen, hopefully, and remind us of what's going on. First thing, chemical kinetics. Again, we're looking at the rate of a reaction. That's all kinetics is really kind of looking at, is how fast the reaction is taking. And you can look at it from multiple perspectives. You can look at it how much a reactant is disappearing. You can look at it from the point of view of how fast a product is appearing. So many ways to look at kinetics. Ultimately, though, the rate of a reaction is measured on how fast reactants make products or use reactants. So depending on what you're focusing on, you can get a little bit different data. But everything is related to everything else, which makes it easy in that sense. And having the ability to control a reaction is very important. There's many things you can use, many different ways you can change the conditions in order to affect the rate of the reaction. Ultimately, if you're in an industry and you're producing some product for sale, the processing time to get from the beginning to the end, if you can affect that in some way, then obviously you want to take advantage of it to make more product to deal with demand. For those of you that are going into econ, you get into supply versus demand eventually. All right, so defining rate, obviously rate is just how much of a quantity changes per given time. So change in concentration over change in time, one way of looking at it. Just like the speed of your car when you're driving, miles per hour. And obviously, of course, there's units involved. Of course, always have to have units to explain what the measurement is. So we can look at it from this perspective as an example. Rate equals the change in the concentration of hydrogen over change in time, which is also basically the slope of a line. So as long as you know how to find the slope of a line, then you're good to go to find rate overall. So getting a little bit more into it, rate of a chemical reaction is generally measured in terms of how much concentration, basically molarity, which you should have seen last year in solutions, or product concentration per given time. So again, another example of a rate expression, change in concentration over change in time. The negative sign is there because iodine in the reaction is a reactant. So the second concentration is going to be smaller than the first concentration. And since it's the second one minus the first one, that gives you a negative number. Rate has to be positive every single time. There is no negative rate. So we tack on the negative sign to our expression to force my answer, if you put data into here, to make it positive. Hence this, as I just got to. I get ahead of myself sometimes. I'm good like that. So here's a reaction, just kind of generally speaking. Nitrogen dioxide goes to nitrogen monoxide and oxygen. You can see there's a relationship between these three lines. If we look at the green line and the blue line, how do they relate to one another? Hopefully you can see that they are going in opposite directions and they are basically mirror images of each other. If we relate the blue line to the red line, what do you see in relationship? Hopefully we see that they are both going in an increasing direction and that NO is actually, the blue line, is twice that of the red line. All of this comes down to ultimately the stoichiometry, your favorite subject last year in chemistry. So again, we can measure the disappearance of the reactants. We can measure the disappearance of the products, all these different, green, blue, and red lines. And they are proportional stoichiometrically. So green and blue, opposites, because one's a reactant, one's a product, but they have the same coefficient. And then blue and red, it's a 2-to-1 ratio. Ultimately, the rate is equal to the slope of the tangent line at a given point. Now, we are not doing the first derivative. We're not doing calculus here, but understanding conceptually that at a given point in a curved line, if you knew the tangent line, finding the slope of that line gives you the rate at that given point. So here's our tangent line, and then you can go from there. Previous exams, the AP exam, students had to actually physically draw this in and do some calculations to find the instantaneous rate at a given point. Change as the reaction proceeds if the rate is dependent upon concentration, but realize that the change in concentration over the change in time is not constant. These graphs are curved. They're not linear. It's a big note to be aware of. Another graph showing kind of the same thing. Hydrogen iodine that I was showing the rate expression with earlier today. Here's a graph of that. We can see that hydrogen and iodine are 1-to-1 ratio, so they should have the same rate of disappearance. But the production of hydrogen iodide, HI, has double the rate of appearance. Other one was disappearance, I'm sorry. So the red line, HI, is increasing at a 2 times the rate as the other one. And it should make sense because the change in concentration, 0.56, right here, and then the hydrogen and the iodine, 0.28. Notice the negative sign is just there to make sure you know it's a reactant, as well as the fact that overall the rate is going to be positive. All right, reaction rate and stoichiometry. So most reactions, the coefficients are of the balanced equations are not all the same. It just happens in the reaction. We have a 1, 1, and a 2 in this situation. Sorry. For these reactions, the change in the number of molecules of one substance is the multiple of the change in the number of molecules in the other. So again, the coefficients is a mole ratio. It enables you to relate the disappearance of one thing to the appearance of something else. Or as in stoichiometry, you can relate any two things you want. Two reactants to each other, two products to each other, doesn't make a difference. So for the above reaction that we saw on the previous slide, 1 mole of hydrogen, 1 mole of iodine, you get 2 moles of HI. So the rate obviously is going to be different. Hydrogen and iodine have the same rate of disappearance, but hydrogen iodide has double the rate of appearance. So ultimately, if you have the expressions, so the change in concentration over change in time, that little fraction, they can be set equal to each other if you just multiply by 1 over the coefficient. So in this sense of a generic reaction of A plus B goes to C plus D, the only time these rates are equal to each other is when you divide by the coefficient. Questions? All right, average rate versus instantaneous rate. Obviously, average rate is over a period of time, taking multiple rates in between that period of time. Linear approximation of a curve. So it's approximation. Big key thing there. It's not the most accurate thing in the world. and the larger the time interval, the more average rate deviates from the instantaneous rate. An instantaneous rate, as we said earlier, is the slope of the tangent line at that specific point. But as you make the time period larger and larger, the average rate goes further and further away from the instantaneous rate. All right, instantaneous rate, again, as we said, is at the specific point on the graph, the tangent line, which again, we've already kind of seen today already, just putting it into words instead of pictures. Yeah, it's the first derivative, but don't worry, we're not doing calculus. All you lovely calc people, go ahead if you want to. I have forgotten my calculus, so I can't really help you there. All right, so back to this graph that we've seen before. Just as an example, we'll use hydrogen because that's on the graph. The instantaneous rate at 50 seconds, that dotted line right there, is as follows. So we know that the change in concentration is negative 0.28 molar. The time is 40 seconds in the way just to get a graph. Remember, you can see the black line, hopefully, in here, where right there is your tangent line. So it's at 50 seconds. It does not mean that I put a 50 seconds number here. It's just at that point, but I need that tangent line. Again, it's over a 40-second period, and you get your answer of, it's on the page. Using hydrogen iodide, instantaneous rate at that exact same point, 50 seconds. Now, notice I'm dividing by 2 because there's a 2 in front of the HI in my reaction. So, yes, I can look at it from the perspective of at that point, they're going to have a similar rate to each other. But realize that in order to make them equal to each other, you have to divide by the coefficient. So yes, HI is still being produced at double the rate, but I can show that they are equal to each other when dividing by their respective coefficients. All right, factors that affect rate. You guys should be familiar with this. Nothing brand new here. Some things, some elements, some compounds, they just are more reactive, or they're just less reactive. Depends on the physical condition that they're in. Are they a big chunk? Are they a solid? So just things do react differently just based on their characteristics. Small molecules compared to large molecules, gases compared to liquids, then the solids. So the way it is physically as well as just what it is plays a role. Also coming down to, surface area, right? Powdered solids are more reactive than blocks of stuff. Those of you that like coffee with your sugar, sometimes, you put spoonfuls of sugar in there versus using sugar cubes. The spoonfuls of sugar, granulated, going to dissolve quicker than a sugar cube. Things are just more reactive. Potassium is a very reactive metal. It's very small. It's it's easy to remove that electron to make it an ion, and it's going to react, which is more so than sodium. Sodium's just a little bit larger, and it's also just, again, properties and different things, if you will, about the element itself. Yes, of course, ions react faster. If I have a bunch of ions in solution, going to react way faster than if the solid it came as has to break down first. So you got to think about the condition in which you are working with. Temperature, increased temperature should increase the reaction rate. Things move around faster, more likely to make collisions, and they're going to react. Kind of a chemist rule, a rule of thumb, if you will. every 10-degree increase in temperature usually doubles the reaction rate. This is not like a question you're going to see on the AP exam, but it's just a good thing to know, a rule of thumb. Again, for many reactions, I've seen a lot in organic chemistry more than inorganic chemistry, which is what we're doing. And then just, there is a relationship that we can look at between absolute temperature, Kelvin, and then the speed of reaction by Arrhenius. We'll look at a little bit later in that equation, which we'll see. You don't have to do any calculations for it, but it does show why temperature can affect reactions. Catalysts. We all know what a catalyst is. Affects the speed of the reaction without being consumed. Huge definition part, as in able to get it back out when you're done. Yes, there's positive catalysts. We don't really use the word positive catalyst because they're speeding it up. Obviously, things can inhibit a reaction. Can be called negative catalysts. So speeding it up, slowing it down, fancy words. But again, realizing, they do opposite things. Homogeneous catalyst, obviously everything's in the same phase. So if you have an aqueous reaction and you use an aqueous catalyst, homogeneous. And then hetero, if you look at a catalytic converter, anyone know what a catalytic converter is? Where do I find one? So in your car, or in cars, they have catalytic converters. And sometimes you hear on the news that thieves steal catalytic converters. Well, they steal them because it's pure platinum. It's a solid piece of platinum. Now, the crap that comes out of your engine is gas phase. All those gases can adhere to the platinum catalyst, allows for a reaction to occur. So after it passes the catalytic converter, it comes out the tailpipe. While yes, it's still bad for the environment, we all know that, it's less bad. I know it doesn't sound too great, but again, it's a homogeneous catalyst because it is a solid piece of platinum, but out of the combustion engine is a bunch of gases. Concentration, again, larger concentration, more molecules, faster reaction. Increase the frequency of molecule contact or collisions. Effective collisions plays a role. Ultimately, the concentration of gases depends on the partial pressure. So a higher pressure, higher concentration for the same reason. More effective collisions, more collisions themselves. And then molarity, higher concentration, lower concentration. Same idea. More collisions, more ability to collide and react. Thank you very much.